All right, so don't be afraid about that one. All right. Okay. Bye. All right. We just had one of the parents just asking about our lessons, and I just had to respond to that phone call. So we are actually live. Good morning to everybody. I know it's Easter Friday, and a lot of the parents are asking, are we not going to church? But we are on lockdown, so we try to do whatever we can in this time. Make sure we make use of every day. Also, please note some of the topics that we are doing now are basically topics that we should have covered in the first term as well. So I am also wary of the time. If examinations needs to be written at some point, we might not have enough time. Okay, we have a problem again with the sound. So I cannot hear the sound, so let me just quickly check what is going on. Is it making a noise again, or you cannot hear anything at all? That's what I need to hear. The first term as well, so I am also wary of the time. Okay, it sounds correct. I just checked now. It sounds correct. There will be a slight static in and out. I think the sound sounds correct. So just check your sound if the volume is high enough, and then I think you should be able to, because I just checked now with the sound and it sounds like everything is going okay. Lawrence, please check again your sound. All right, as you've said, wary of time, and we would like to get as much topics done as possible, so that when classes do resume at school, then we know that we have covered at least some of the topics, and we can focus on revision and other things as well. So that's what we have. So to start off, as we normally start, we would like to start with a prayer. So let us just pray together for the sessions of today. Oh Lord, Heavenly Father, we thank you yet for another classroom session, Lord. Father God, we thank you that you have allowed us to be able to learn. And we thank you, Father, that you remind us this time, Easter weekend, Lord, that you have given us so much. You have given us your Son, Jesus Christ, so that we may be able to live eternally, Lord. Amidst everything that is happening in this world, we trust you that your word remains true and it never changes. Father God, we pray for all the learners, that they will continue to have this spirit of learning, the spirit to become better human beings, self-sufficient in the future. Lord, we pray for our nation. We pray for the world, Lord, that you be with each and every person, that you guide them, lead them, and comfort them, Lord, where they have experienced losses in any form or another. We also pray for wisdom, Father. Give us the wisdom to help fight this pandemic, and help us also to find answers to questions that we do not have at the moment. We pray all of this for Christ Jesus' name. Amen. All right. So I do believe everything should be fine. If you are on the Facebook channel, and again, if you have any questions, queries, or if the sound is not very clear, please just type in there as well, so that we can work together. This is not a lecture, it's an interactive class. So I also expect you to give me hints or questions or comments on how we should improve this class as well. So to start off today, we are looking at our vectors in 2Ds. The last lesson that we had, we gave you some homework, and today we would just like to look at the answers of that homework. The homework had two phases. There was a question 1 or section A and a section B. Section B was a bit more challenging for those higher level students as well, but section A is also there. For those who did not really understand section B, that is basically what the lesson for today would be at. So we will try and understand how to get those answers from lesson B as well. But I will not be explaining the methods in the during the correction times. We will be looking at those methods during the lesson as well. So let's just look at the questions that we had and also the corresponding answers. So I will be commenting a little bit on some of these answers that are there as well. So for the first part of the question, we looked at this part here where we have a vector represented, and we ask you to basically write down the column vector of this vector here. So we follow our row by column. So we said that our rows go from left to right, and you have, if you looked at this one, you could have counted the blocks 1, 2, and then you write in 2, and then we look at the columns goes from up and down. So then we look at the columns. We can start from the bottom one here, 1, 2, 3, and then we write in our 3 over there. Okay, so let me just use the highlighter so that we can see what I'm talking about. So we had 1, 2, 3 over on this side, 1, 2 on this side, and 3 going up and down. Either way, you can start on this side or you can start on that side. So we looked at various methods how we can come up with this one. Remember, I said that we start from a given point of the vector by moving our origin to that point. So the origin is the 0 on this side, so we moved it to this side, and then we can count clearly. If you do not like this method, we said that we can use our change in y and change in x to find the magnitude of the vector. Alright, so now we have found the values, but we did not actually look at the direction as well. So please note, when we count our column vectors or our blocks, we are not looking at the direction. We are only looking at our size, right? And now we have to go to the arrow, and we see that the arrow is pointing in that direction over there. And for that arrow, we have to go back and remember our revision previous lesson that we did. We looked at a what we call a directional arrows, what each direction of the arrows entails as well. So let me just see quickly. Yes, so this is basically what we refer to as our directional arrows, and they give us a brief understanding or a solution to how our vectors answers should look like. So positive row, positive column if it goes in any of the directions, and in this one it's just a little bit we have on the screen, so we have to take note of the first quadrant, second quadrant, third quadrant, and the fourth quadrant as well. So this is what we have from the previous video, and we will always come back to this image here to guide us regarding how our vectors should basically look like as well. So just take note on that one. Okay, so we continue from this one. So that's just basically the explanation. So I'll be going a bit faster now with all of the other ones, and you can always compare and go back using the methods that we have done as well. So for myself, I do know how the what we call the directions are of the quadrants. I've memorized them. That's a very important thing to do, and now I can answer most of the questions quite easily as well. So without any further ado, let's just continue. So in part 2, we again have a vector here. All right, so we follow the same steps. Okay, whether we start at this point or we start at the other point, it does not really matter. So in this case, we will start at this point because it's the first one to my immediate left, and then we will count the rows and then we will count the columns. So first the rows, in this case I only have one block, so that one block I will write it in as my row, and the columns going up and down I will write it as, count again, 1 2 3 4, and then I write in a 4. And if you note, there's an arrow which gives us the direction, and that means I have to go back to my direction arrows and what they tell me. So in this case it means that we will have a positive on top and a negative at the bottom, so I will add the negative. Please note the methods we are using, or what I am trying to teach you, is that when we are dealing with vectors, there are basically two steps that we need. So the first step is we need to calculate the magnitude, that's the size, and the second step is that we need to basically find the direction. So you cannot solve a vector by only doing one method. Okay, we have to do two things, because we said it has both size and direction, magnitude and direction, so we need to do two things and not one. So that's mostly where some of the learners get confused and missed some of the answers there. They only do one step and then they miss the other one. So remember, we have to do two things. Yes, it's a little bit lengthy, it's long, but it's very important in terms of what we will be doing as we continue on. So remember, we have two steps. So I always do the first step, which is the easy ones. We count the blocks and then we go and check in our diagram where our negatives and positives should be. So in the first third one we'll have the same, so that's the answer that we have. Please take note of the arrow. The arrow points in the direction of negative, negative, so both our answers will have negatives. And then we continue. There's one that I would like to focus on, especially that's number 8 and number 6, because we did not mention any of them there yet. So when we look at number 8, which is over on this side, we have a very awkward vector here. Now we've said that we are always going to start counting a row, but in this case our vector is only a single line, so we do not have a row appearing there as of yet. So if there's no row, because we cannot count blocks here, if there's no row, we just put it as a 0. So our row will become a 0 in this case. And then we look at our columns. So our columns, at least it's moving one block down, so we will say one block. And in the arrow, remember we said if it goes down, it becomes a negative. So that's an important bit of information you should also look at. So it goes down, it has a negative. Okay, that was one of the last questions we also looked at in the previous slide. And then on number 8, please note that this one where we had to draw in the vectors, starting from 7, we had to draw it in at some point. Please note that the answers here, when we ask you to draw in a specific vector without giving you a start coordinate or such anything like that, it means whether you drew your vector on this side or even if you drew it somewhere on this side, that is still correct. It does not matter where you draw it, as long as the magnitude and the direction are the same. That will be the basis of our lesson today as well. We will be looking at some of these vectors that we call equivalent vectors. So vectors that are equal. So when we are drawing a vector and we don't give you a specific coordinate to start, it does not matter where you draw it, as long as the magnitude of the vector and the direction will be the same. We will talk about that briefly after the corrections. And when we look at number 8, as we've said, in this case, this vector is just a horizontal line, because we do not have any columns for that vector, so we will only look at the rows. So row says -6, so we'll have 6 blocks that we must draw the line with. And after you draw that 6 blocks, then you will have to now look at the negative sign and say, okay, that will tell me where my directional arrow should go. Please note, 0 does not have a negative sign, so we cannot put a negative at a 0. It does not make any sense. So we will only focus on that one. So we can look at 0 as being a positive. Okay. So with the negative sign, we know that the horizontal line decreases towards the left, so the arrow points towards the left. That is an important bit of information that you should also take note. So the arrow points towards the left. And then the last one, we have -3 and -3. So again, we will count 3 blocks, 1, 2, 3. That's going this side, going up again. We can also count 3 blocks, that's 1, 2, 3. And then we look at the arrows. Every time you count, you write it in. So I start with the row, write in the row. Then you go to the column, write in the column. Then we go to the arrow. So the arrow is pointing in our negative direction. So both our answers here should have a negative and a negative. Okay. Based on that, we move on to some of the other questions that we may have had. This ones we try to put in a comprehensible input to challenge some of the smart students a little bit, especially our higher level students. Sometimes the way I'm explaining will be a little bit too slow, because we are trying to cater for everybody. So we try to put in some difficult questions a little bit. It's only difficult until you understand it. So with this ones, we ask a question, draw the sum of the vectors. So we give you 2 vectors here. For the ordinary guys, I said that you can just draw in the 2 vectors that are here. So you could have drawn in 2 vectors, which are the red lines that we have here. If you have drawn in 2 vectors like that, that would be normally fine for now. But we will look at sum of vectors, adding vectors and operations of vectors in today's lesson as well. So this is the correction for the students who try to attempt this question. We will come back to it again later on, just to see how we can use what we have learned today and apply it to this type of question as well. So we would also like to put up some exam questions on vectors, just to see how do we ask them in examination as well. Alright, so I believe we have now exhausted the corrections a little bit. Remember, we will come back to this one, and I will also post the corrections on Google Classroom for those who would like to download it and just go through it as well to compare your answers as well. So don't worry about that so much. Alright, so let's look at our lesson for today. And before we start with today's lesson, we always make an announcement on what it is that you will need for today's lesson. So for today's lesson, you would basically need your notebook and a pen, as we are doing some calculations and workings as well, so that you can have notes for yourself. It's always best to write down everything that you learn. All right. Also, we will look at revision, what we have covered so far. Okay, the corrections helped us a little bit, but let's just look at it again. So we spoke about scalar quantities, and then we also spoke about the term magnitude as well there. And when we looked at what a vector is, which is basically the definition of a vector, we said that the vector has both a magnitude and a direction. All right. Now, I would like to spend a little bit of time on this term, the magnitude, because I've also realized recently that we are using a lot. We are using the word magnitude a lot, and that sometimes by using that word a lot, it becomes confusing to some of the students, and it causes a little bit of a problem in terms of if we say calculate the magnitude of the vector, and then we tell you in the definitions that the magnitude the vector has both magnitude and direction, so it becomes a little bit confusing. So when we are referring to the magnitude in the definition, only in the definition, we are referring to a word called size. So we just want to mention size, like it has a size. All right, it has a number attached to it, it has a value. Okay, a value would normally be a best description, but we don't only want to use value, we want to use a length, size, something that is measurable. That's basically what we say. We want to have a size here. So in some examples we will refer to the definition of the magnitude, the definition of a vector. The term magnitude here refers to size. So I think I can just also add it in shortly here, so that we understand it as well. So we will refer to the definition of a vector as a size here. So I hope it makes a bit of sense. So we will say a vector have both size and direction. Okay, so size and direction, that's what this word magnitude will refer to when we are defining a vector. Okay, so there must be a size and there must be a direction. All right, and then when we look at the next slide, and which will be also the basis of what we will be looking at today, now you see there's another word again, which is magnitude. We will come back to that. We talked about vector notation. We can write it as a displacement vector, PQ, with the arrow on top, or just a P itself, okay, or a letter by itself. And then we spoke about also again the magnitude of the vector. That was now again this magnitude that we are referring to here is not the one in the definition. Okay, not the one in the definition. This one refers to our length. Okay, the distance between the 2 points, the distance between point P and point Q, that 8 kilometers that we have there. So this one, this magnitude, if I can also just add it into the slide. So this magnitude that we have here will be our distance. Okay, so that will be the distance between the 2 points. Remember the other one we are talking about a size, and now we're talking about a distance, okay, or the length of PQ, as we have said here at the bottom. Okay, so do take note of that one as well. We have that word magnitude coming up a lot, so that we don't get confused about magnitude, and every time it's just magnitude. Okay, so one we said will be the size that is in the definition, and the other one we are saying now we are calculating the distance between the 2 points. All right, so that was a revision of last lesson, and then this is where we basically stopped at, looking at the column vector, how we represent our column vectors. We have counted the blocks, and you would have noticed that in this slide we don't have a Cartesian plane, which is also very important, that we should not always focus on the Cartesian plane, which means the x-axis and the y-axis. Sometimes we just give you a block paper and a vector, and you have to find the column vector. So just worth mentioning, why do we call it a column vector? Okay, so why is it called a column vector? It's because of the way we represent it. When you look at this one, we have like a number at the top and a number at the bottom. I've mentioned that before. at our last lesson, where we mentioned that there's a number on top and a number at the bottom. So top to bottom, if you remember, our columns go from top to bottom as well. So we have a column going from top to bottom as well. So that is our column, how we represent our column vectors as well. So just take note of that one. It's called a column vector because we are representing it as a single top and bottom numbers without any division sign. That's where the word column comes in. It's represented in as one column. All right, but we find our columns also on the Cartesian plane, okay, because it's a table. So also these words that are similar or that we use over and over again, sometimes they have a tendency to confuse learners. So just take note on that one as well, so that we don't get mixed up with the words that we have. All right, so we continue. Today we will be looking at operations of vectors, and we will start with calculating its magnitude. That would be the distance between the 2 points, okay, and we will look at vector addition and also vector subtraction for the rest of the lesson. So we will start with magnitude. It says here, by Pythagoras Theorem, the magnitude of the vector is given by the following. We have said the absolute value, remember, of this one, st, is equals to the root of 6 squared plus 7 squared, which equals to the square root of 85. So let's explain what all of this information here really means, because it doesn't make sense now just giving a formula without any explanations as to what is going on. So for that we will be visiting our old friend, our board, and let's just move to our board. So we are basically looking at, we want to calculate the magnitude of a vector, that is the distance between 2 points. Let me just put down the 2 points here, point A and point B, and we said this is a vector. So for this case I will be using a positive vector. It does not really matter. Okay, so just trying to make it a little bit bigger so that we can see a bit clear. So let's say we have a vector here, AB, all right, and we want now to find the magnitude of this vector, the distance between point A and point B. Now, in order for us to look at this one, we need to go back to something that we have already done before, and that would be drawing. Okay, now we have it. So something we have already done before, and that is our Pythagoras theorem. So within our Pythagoras theorem we have a right-angled triangle. Okay, my letters are slightly a bit different here. Our B and our C is different, so I will write the formula based on the information that I have here as well. So in order to write down that formula, it will be the following. We will say that a squared, a squared is represented as this plus b squared. In this case it will be c squared, will give us our b squared. Okay, so so this is now the Pythagoras theorem of this triangle that we're having. So in Pythagoras theorem, we are saying that if we draw a square on this side, okay, I'm going back now a little bit to the lower levels for those people who are doing core. If we draw a square on this side using the line A, okay, and we draw a square on this side using the line C, and we draw a square on that side using the line B, we would find out that if we basically find the area of this square, find the area of that square, find the area of that square, and if we add these two squares, it will give us the area of the largest square here. So that's basically what Pythagoras theorem is telling us about. Now, what does this have to do with vectors? We have noticed that our vectors are basically lines that are represented almost most of the time in a diagonal form. So this line C, I can change it into a vector. Line A, I can change it into a vector, and line B, I can also change into a vector. That's basically what vectors has introduced. Okay, so if we want to know the length of AC or BC or BA, in whatever way we're looking at, we will make use of the Pythagoras theorem, which is this one here, to apply to our formula here. So this is what I've mentioned the last time, that we have to use some of mathematics or some parts of mathematics that we did before. So that would be now here what we are going to use. So let's go back to our vector itself here, and by looking at our vector here, we have noticed that it's just a line, but we can change this line to fit our Pythagoras theorem. So how do we do that? We can basically add a few lines to it to make it look like a right-angled triangle. Okay, so I've added two lines here, line F and G, which has no particular value itself, but we do know that this line that we have drawn represents our column, correct? If we had to write this in vector notation, this represents our column. So we had how many blocks? 1, 2, 3. So F has a size of 3, and the same with G. 1, 2, we have 1, 2, 3. So this line G also has a size of 3. So this shows us that our vector AB would have had a column vector of a 3 and a 3. Okay, so that is our vector notation in column vectors. And please note that the arrow is pointing upwards, which means both values will be positive. Okay, so 3 and a 3 are both positive, so I'm fine. I don't need to change anything here. Okay, so that is how our column vector would have been, correct? So now you can see that using this right-angled theory, we can now also find use Pythagoras theorem to calculate what u will be. What is u? So we know F is equals 3, G is equals to 3, and what is u equals to? So u is not having anything, so I will just put a u there. So we want to find u, so this is where Pythagoras theorem comes into place. Okay, so Pythagoras means, in this case, I will modify my formula. Please note that the correct formula says it should be, let's just use the text because it will be better to use the text. So within our text here, let me just see if okay, let's not go to advanced. We say normally our formula that we all know would be a squared plus b squared, which will give us c squared. That is basically what most of the textbooks refer to the Pythagoras theorem. Alright, we did modify it a bit earlier to fit the diagram, so we should also modify this formula to fit this diagram. We cannot just use here. There's no A, there's no B, there's no C. So we need to identify what value would be our A, what value would be our B, and what value would be our C in this case. So the values that we are looking at now, we only have F, G, and U. So the C value, we have always been told, is the longest side. That's the longest side that we have. So that would be our C value for the longest side. So right now, our longest side is the U, so we will replace the C with a U. Okay, just take note of that one. The C will be our U. Okay, now we need to find the A and the B. So A and the B is just any of the other two sides that we are having here. So it does not matter which one you use, it will still be the same thing because we are adding it up. So we can either say like let the A be the G and let the B be the F. So we will have an F there. Okay, just to make it like this. So let me just write now the new formula incorrectly. So we are saying we will have a G squared plus a F squared, which should give us a U squared. Okay, so that is our new formula that we have now based on the Pythagoras Theorem. So G squared plus F squared equals U squared. Okay, so that is what we basically have now in this term. Okay, so after you have get your formula correct, we can now just substitute the numbers into it, and then we can find out what our answer will be. In this case, our answer, if I can just also write it in here, we know that the G equals a 3, which is squared, and in our case, evidently the F is also a 3 squared, okay, which should give us our U squared. I'm only writing the complete formula now, but as we continue, I will not be looking at the complete formula all the time. Okay, so because it takes a little bit of a long time to type on this board. So we have 9 plus 9, which is 18, and that will be equals to our U squared. Let's put in the U squared, and then we will have it there, and I will stop there for now. So in this case, this just seems to be, just put some enters into it and set up. Okay, I tried to do it a little bit, but it doesn't want to do the correct thing, so let's just keep it simple and add another text box, just so that we are all on the same space. I don't know why it's going into lexic. Okay, equals to U squared, which equals to 18. Okay, there we have it. So we try to square the threes, which will give us a 9. So we're saying 9 plus 9 should give us the U squared, and the U squared is basically our 18, which equals to the U squared. So if 18 equals U squared, means we still haven't found U. U is squared, so we have to find the root, the square root of 18, which will give us U. So that's the final part of the Pythagoras theorem. We will have to find the square root of U. I think the formula should be like this, if I'm not mistaken. Let's see if we'll pick it up. So the square root of 18 is basically what U is equals to. Now, some numbers are not perfect squares, so if we have to write it in here, you can leave your answer as square root of 18 as well. So we will mark that one correct. So that would be the magnitude of of this vector. Please note, the reason why we always say that our magnitude is a positive number is because when we are dealing with square roots have two possible answers. One answer can be a negative answer and the other answer will be a positive answer. So we don't want a negative answer for distance. We've mentioned that one in the previous lesson again. So whatever answer we get from this square root of 18, you will get a negative answer and a positive answer. There will be a plus minus. We don't want the minus answer, we only want the positive answer, the plus answer. So that is basically what we are applying here with in terms of the magnitude of a vector, the distance between the 2 points. So just to recap again what we have done, we had a vector AB, okay, or U, and we were asked to find the magnitude of that vector, which means the length of AB, and we added two lines to make this vector into a right-angled triangle so that we can be able to use Pythagoras Theorem. So after we've used Pythagoras Theorem, we found out that this answer is the square root of 18, and we said that if you are asked to give your calculator's value, please just leave your answer as a positive answer, correct to certain decimal places if that is required as well, and then you leave your answer into those decimal places how it is. Okay, just also looking at the comments, there was a question on the syllabus for y equals to mx plus c. The syllabus I will post on the Google Classroom as well if you need them, both grade 12 old curriculum and new curriculum grade 10 and 11 as well. So we will post both of those questions, both of the syllabuses on there. So let's just go back to our main slide here. So this is basically where we found out that our magnitude is now represented as the root of 6 squared plus 7 squared, and you can see now the 6 is represented as our A and the 7 is represented as our B squared. So that is now basically where we are with the 7 and the 6. Okay, so we drew in an imaginary line here and another imaginary line going up, and it changed it into a right angle, and we use now our values that we got from the rows and the columns to use Pythagoras Theorem to calculate this distance between S and T, and that's how we end up with this value here. Okay, this is the easy method that we have. Now we have another method. This is basically the whole explanation of our column vectors in terms of what values we have. Okay, just a cleaner description of our magnitude in terms of our column vectors. Okay, there's one more thing I would like to mention, and which we will not find in this slide here. So I will go back to our drawing board, and in our drawing board we will be looking at what if we have a set of coordinates. Okay, so this one would be a little bit lengthy because it has to do with what we discussed in the previous lesson as well, about how we can represent our vector as well. Let me just make it into a vector. Okay, okay, so we have a vector AB which is there, so you can see our vector is represented as the 4 and the -2. All right, now why am I coming back to this one is because I would like us to look at making use of our coordinate system to basically come up with a formula to calculate the magnitude of the vector. So let's say, for instance, that we did not give you this information over here. We did not give you the column vector, okay? But we gave you the coordinate systems. We gave you that point A has a coordinate of this, point B has a coordinate of this. Calculate the magnitude of the vector. So using coordinate system, how will we go about it? So in this case, we will follow the same principle. We do know that we have a square root of something that we need to do, correct? So let me just try and see if we can do it in lex. So what are we given now? If you remember the last lesson we looked at, we mentioned that we can find our rows and our columns by looking at the change in x and the change in y. Okay, so we said that it will either be our rows, which is this one here, will be the change in x, and our columns will be the change in y. So we can also use that formula in this description here to try and give us a answer to find the magnitude of the vector. So if we look at, I'm just going to write it down. So we said that it will be the change in x and the change in y. So we will have x1 minus x2, that will be our change in x, and we are going to square that change in x. Okay, so it's x1 minus x2 squared. That will give us the rows squared, correct? And we are going to add that one to our change in y. So it will be y1 minus y2, and that is also in a bracket, and we will square it and we will close off the bracket. So if we square those two and find the square root of it, then we will basically find the AB that we are looking at, the magnitude of AB, which is the in our formula here. So here I've written down the formula that we will be using. So in this case, I'm saying it's a square root. I'm abbreviating to SQR for square root. On my keyboard, I don't have the square root symbol. We can use a calculator later on, but I don't want to use the calculator now, but we can also use it to find now the correct answer to this one. All right. So if in our calculator, we said we are having the square root of our x1 and our x2. So here are our coordinates that we have. Before I go on, please note we can also reverse it. It can be x2 minus x1, y2 minus y1. You will still get the same answer in any way possible. So to find the magnitude of vector AB using our coordinate system, we are not going to use anything else. So over here I have my square root, which is this one here. Now I need to put in my coordinates, the change in x, the change in y, and square that one. So for that we will be using a bracket, which is our bracket is there. So what is the first x coordinate? I can use -7. Okay, -7. All right, space, and then we have minus space. What is the other one? -3. Those are our two x coordinates. Okay, so -7 minus -3. So this one is putting it into as a plus, because a negative and a negative makes it a positive. Even if I put in a bracket here, it will still put it as a plus. But with squared numbers, it does not really matter. It doesn't really matter whether you have a positive or a negative. So I need to square that one, so I square it. Okay, so you can see that my change in x and my change in y, let me just try to pull this a little bit bigger so that we can see. As I'm applying this formula that we just wrote down in our calculator, you will see that it already gives me a 4. So it noticed that the change in x, change in y is a positive, which is a 4. We square that, okay, but it's already taking note of the root as well. So we have a 4 inside. The square root of 4 is the square root of 4 is 8, and the root will be back to 4. So let's continue our formula. We have that one, and we said we are going to add it with sorry, there's a small arrow here. Let's just go back to this one. That plus and not this one, because this plus is in the square root. So our next bracket is our change in y. So we have the y1, which is a 5, minus the y2, which is a 3, and then we said of all of which we have to square. Okay, so now we have found our formula is complete. And then we have the first bracket, which is a negative number here. It does not really matter. It will just subtract it, get a 2, and then we find the square root. So now you can see it has calculated the magnitude, or that is the distance between A and B, as 4.47. Okay, this is normally how we would punch it in our calculator if we are making use of this formula. Correct. Now, just to see whether or not that is true, we can try and put in the normal one, which is basically saying that we have the square root of the following one, which is our row, which is 4, and then we say 4, and we square it, and then we also say plus our column, which is negative 2, and we also square it. Okay, and please note there must be a bracket for negative numbers, so that the computer can understand, oh, we are square rooting the negative number and not the 2 and then minus it again. Alright, so you can see that our two answers here are exactly the same, 4.47, 4.47. Whether we use the column method or we use the change in x and change in y, the coordinate method, we still find the same magnitude of this vector. Okay, so in some cases where our vector, so I'm just going to draw this a vector here, let's call it CD. So in some cases where we have vectors that have one of the things as 0, we just want to see, can we still find a magnitude of this vector, the distance between A and B, by applying this rule here. Yes, we can still find it even if we use a single vector going in this line. The magnitude of the vector, the distance will just basically be the blocks. All right, it will just be our, in this case, the magnitude will be the columns, which is 1 and 2, and here we see that the rows are 0, so we factor out the rows. We will just work with the column, and we will change that to a positive. Now the reasons for the Pythagoras theorem is that when we are squaring this, let's just do it so that you can see. We're saying now, if I use the same method as I've used before for our new vector CD, we said it's the square root of what is our row. The row is 0. All right, and we can also, let's just complete the whole set, 0 squared, and then we said plus, what is the other one now? We have a bracket for negative 2, and we also square that negative 2. Okay, so that is basically what the formula will look like. If I press enter, you will see it just remains a 2. Okay, so what that did is it took this 2, which was a negative, and remember we said we have to work with an absolute value. So an absolute value means that all the negatives will change to a positive. So we took that negative 2 and we just made it a positive 2. So that will be our magnitude of this vector. So we can do that also for another vector. Let's go into the negative quadrants here so that you can see it does not really matter in which quadrant you are. So in terms of W, let's just also go a bit down. In terms of W, if we have to find the magnitude of this vector here, okay, for W, let's use the coordinate system, okay, coordinate system, so that we can also see if it's just a straight line. Okay, for this one, whether it's going in this direction or other direction, if it's a diagonal line, it will always be the same. So for this example, we will use the coordinate system. So we still said it will be the square root of what is our change in x and change in y. So change in x, we have the first one, which is a negative 10. Too many negative numbers, sorry. So we have a negative 10, okay, and we are subtracting the negative 10 from a negative 7. So that is our x1 minus x2, which we have here. Okay, so x1 is 10, that's the e, that's the 10 there. X2 is negative, x1 is negative 10, x2 is negative 7, and I've written them in this one. And at the end of this bracket, we have to square it. That's correct. So we will square it. So after squaring it, we will add it to the change in y. So what are we changing in y? So the change in y will be, the first y is a negative 3. So I'll put a bracket for that negative 3. And then we are subtracting it from another negative 3. So I will also put in a bracket a negative 3. So that is the change in y, negative 3 minus negative 3, and we also basically square that one. So please note, a negative times a negative gives you a positive. So negative 3 plus 3 will give you a 0, and that will be the 0 squared that you see in this side again. So that is what we have, and after that, if we press enter, we get a 6. Okay, so please note, it is sorry, the formula here is not correct, you see here. Okay, let's just correct that formula quickly. This is supposed to be in a bracket, and this is not supposed to be a 2, it's supposed to be a square. Oh dear, it went now a little bit too far. Okay, let's do that one again. I think that the formulas did not work out correctly. First, we take our vector back. Okay. Just have to be careful with this calculator. So we said we have our change in x, so I'll just put in a bracket here first, and that bracket will have a square, and then we will have plus another bracket which will also have a squared. Okay, that is what we need, and within this bracket we put now our change in y. So the first one is a negative 3 minus another bracket which also has a negative 3. That is what we want. And then in this bracket we have the change in x, which is negative 10 minus another bracket with a negative 7. Okay, so this one should do the trick now, and we have a 3. Okay, so this is the correct method. So please note again, the difference between this one and this one is a positive one. Okay, it's going to the positive side, and the other one is a negative, which is going down. So that's the only difference we are having between these two. However, I've also changed the methods. The first one, I used my column vectors, the numbers that I have in the column vector, the 0 and the -2, which I put in the equation. This one, I've used the coordinates that are given, the E coordinate and F coordinate, which is in this one. But the main purpose that I would like us to deduce from this one is, if we are dealing with a vector which one of the row or the column is a 0, our magnitude will just be that number that is inside that column vector, the positive number, not the 0. Okay, so in this case it is a 3, so the 3 is just the magnitude. In the other case, on top with the -2, we cannot have a -2 magnitude, so this -2 changed to a +2. So that is the trick that I would like to mention on the magnitude of the vectors. Alright, so we have exhausted a lot on the magnitude of a vector. We have explained it. I'm just revising what we have done. We have explained that we can find the magnitude of a vector by applying Pythagoras Theorem. We use our a squared b squared by making a right angle triangle. If the vector is a diagonal, pointing in a diagonal direction, we make a right angle triangle. If the vector is just a straight line vector, which means it's just going in one line, vertical or horizontal, then the magnitude of that vector is either its column itself or the row, because one of those rows or columns will have a 0. So we do not factor in the 0. We just either take in this case the column, and in the other case the row, and we make sure that that number is a positive number, because the magnitude must always be a positive number. So I believe magnitude of a vector should be a little bit simpler now, or easier to understand, and we can proceed. And just to remember and rephrase what we have said, in this case the magnitude that we are referring to is the distance between C and D, distance between E and F, distance between A and B. Okay, that is the distance. Okay, the distance, the length of the line, that is the magnitude we are referring to. Okay, so please note, for straight lines, if we refer to it as the distance between C and D, then you can just say, oh, it's 1 and 2. There are 2 blocks. That's the 2 distance. So you will see here, CD, the magnitude is 2. The distance between E and F is 1, 2, 3. 3 blocks. So the distance is 3. So that's the 3. Okay, so that's what we have. Please do take note that in the coordinate system that we are having, even if you are working with -10, -7, all those negative numbers, they have no effect on our vector here. Our vectors remain the same. However, in this case, for our vector AB, if we look at the distance, we cannot count the blocks. We cannot say 1, 2, 3, 4. It doesn't make sense, because the line is diagonal. Okay, there's still some extra blocks here, some extra part here, which could be a fractional part that is here, and you can see that that extra part is where the 4.7 comes in. So we need to use Pythagoras Theorem, which will give us the diagonal line correctly. So I hope that if a question pops up regarding the magnitude of the vector, you should be able to get it correct. Alright. Also, just looking at some of the questions, it says it's a little bit blurry. Okay, there's a question. Let's just look at quickly some of the questions that are here. The first one was the quality is a bit blurry, so I hope it will be improving. It does not seem that I've lost any connection here. If your quality is at 360p, okay, you can just increase your quality, because I'm also looking at a live feed. Mine is in HD, so in HD it's showing a little bit better. So just increase your quality on your device. There's a setting there on your streaming that will allow you to increase the quality. And there's another question here from Eleni. Are you able to provide a real life situation in which we can is it supposed to be apply vectors? Okay, so I was actually thinking about the real life situations. How would we explain vectors to you in real life situation? The best situation for us to do vectors that I can think of, not in industries or other applications, it's actually sports. So if we have a sports game, any sport, we apply vectors. You just did not know. In Namibia, we don't have a very successful soccer team because apparently we cannot score goals. So basically applying the methods of vectors, even if we look at A, B, A can be player A, B is player B. Player A needs to pass the ball to player B, but he needs to know what the distance is from A to B so that he can apply the correct pressure onto the ball, okay, so that it reaches player B and it's not intercepted somewhere by the opposition squad. So passing accuracy, okay, passing direction, and passing distance of a football player. It's also applying vectors on the soccer pitch. And if you look at adding, when we look at adding different vectors, you will notice that in order for us to score a goal, we need to basically pass the ball between player A to player B to player C, and then player C is the one that needs to score the goal. So in that way, we can now see, okay, this is how the ball moved from A to B, from B to C, and then from C to goal. If you also look at a very good example of the squad that applies vector method is Barcelona FC. It's not my favorite team, but their passing accuracy and passing abilities is applying vectors. And now all the other teams do not understand what is going on. Why is Barcelona able to pass the ball in such accuracy with such speed and precision? This is all due to their training that they are doing. When they get training, they also train with mathematicians, and then they teach them vector methods, the speed of the pitch. Please note that a football pitch is having a fixed length and a fixed breadth, and they are able to pinpoint distances. If you are in this position, the distance to that position is approximately this. This is the force you need to apply to the ball in order to make sure it reaches the opponent. So that's why these guys are very highly trained, they are skilled, and they also get paid a lot, because if you are able to understand vectors on a football pitch, you will be able to do amazing things and even score goals in ways that you didn't even know it's possible. So this is also why it's important. So I hope I've given a very good real example of vectors applied in real life situations for Eleni. Alright, I believe we have covered magnitude in detail, so now we will proceed to the second part of our lessons, which is now looking at some of the vector operations and things like that. Before we go to operations, there is a short lesson that we need to look at as well, and that is in terms of our equivalent vectors, or vectors that are equal. Sometimes we will ask you to indicate which vectors are equal and which vectors are not equal. So here is a quick statement that states that two vectors are equal if they have the same
Okay, remember we said magnitude is referred to as size, so it will have the same size and the same direction. Then we can classify a vector as being equal if it has the same size and the same direction. Okay, remember I'm referring to magnitude as size. Okay, if it has the same size or magnitude and direction. Okay, so in this case our magnitude or size means the same length as well and the same distance as well, in the same direction. Okay, so the vectors that we have here in this demonstration here, they all have the same magnitude. Okay, this vector here has the same magnitude as that vector there, has the same magnitude as that vector, has the same magnitude as that vector, has the same magnitude as that vector. Okay, so the magnitude, if we have to use Pythagoras Theorem to calculate all the magnitudes of these vectors, that's the distance between the points that we have here. Okay, in this case there are no points, it's just a single vector represented, but we know we can draw a right angled triangle in this case here and calculate it. The same with this one, the same with this one as well. Okay, so they all have the same magnitude, but not all of them are in the same direction. Okay, so with AB and CD, we see that okay, they both have the same magnitude and they both go in the same direction. So these two magnets are vectors are equal. So these two vectors are equal. Okay, when we look at vector P, it's not in the same position. Okay, remember we are not looking at position, we are looking at magnitude and direction. So vector P also has the same magnitude and is pointing in the same direction as D, vector CD and AB. So this vector P is also equal to these two. However, the vector R and the vector Q, they have the same magnitude, but they are pointing in different directions. So these vectors are not equal. Okay, so R is not equal to Q and Q is not equal to P, which makes R also not equal to P. Okay, so this is a very important observation. As we continue with our operations, our equal vectors will pop up again in one form or another. All right, so we will look at some examples again shortly as we continue. So just take note on vectors that are equal. It must have the same magnitude and it must be in the same direction. It does not matter on which part of the quadrant of the Cartesian plane it is, as long as the magnitude and the direction is the same, that vectors will be equal. All right, so another way of vectors that we can also look at the differences between them is referring to opposite vectors. In the previous lesson, we had one of the students who noted that in our quadrants that we drew, that there are some positions that are opposites of each other, and this is also what we are explaining now. So we are basically referring to what we call opposite vectors, or vectors in opposite directions. This is how we depict it. So here we are looking at bearing, and in bearing remember that we spoke about, we are looking at an angle in that direction. So this one would have read, if we are looking at the bearing of Q from P, then from P we will look at our north line and see that angle there. That's the bearing of Q from P. Okay, And if we look at the bearing of P from Q, that is the one we are looking at in the next image on this side. So this is basically an indication of opposites. If we are going in this direction for one and we are going in the other direction for the other. So if this direction has a magnitude of A, or let's say the magnitude is A, and then in the other direction we will look at also a vector with a magnitude of negative A, because it's the inverse or the opposite or the other side of this vector. So PQ is opposite direction to QP. Vector QP is opposite direction to the vector PQ, but has the same magnitude. So the magnitude remains the same, but the directions are opposites. Okay. Remember that we said when we are looking at magnitudes, we will not have a negative number. The negative will fall away and we will just remain with a positive. So in this case, this negative that we have in front of the A, if we are dealing with magnitude, will disappear, and for both of these vectors we will just have A. It says here, hence PQ, the vector PQ equals negative the vector QP, or A equals negative A, which will be in a bracket positive. So the negative of that opposite vector. Okay, does not make a little bit sense here. So let's go back to our drawing board so that we can explain a little bit in detail what is going on. So in detail what is going on. So for starters, let's look at a vector. In this case, let's just draw one here, a B, and let's make it a vector. Okay, so in this case I have a vector U. In this case, let's call it U, and we are looking for the opposite of this vector. So in most cases, when we are dealing with any opposites of anything, if we have let me just see which letter would be easier to write. Let's look at B. Okay, if we have B here and I want to find out what the opposite of B would be, so that will basically mean we need to have a mirror image of B. In this case, I cannot draw the mirror image, but I think you have an idea. When we deal with transformation, you will see that we will come back to these things here. So what I'm looking at here is basically the opposite of this shape and this shape. It's supposed to be the same shape, but it's not. Okay, maybe I can use a different program for that. Let's just see, just to explain it a little bit better. Okay, okay, I'm just trying to see if I can use a image that would be easier to explain and also easier to look at. All right, so and then we can look at it together as well. So what we have here, okay, let me just put it on so that you can also see. We'll just remove that one and we will add a new window. Let's see. Okay, so let's look at it in this this sense. We have two images at the moment. So these two images that you see here are basically equal to each other. There is no difference. All right, So if I want to find the opposite of this image or the inverse of this image, I will basically have to flip it over like so. So I hope you can see it a little bit better. So what I just did is we had an image, okay, which was the same image, our Google Classroom image, and then if I flipped it over, then it becomes an image. So this is image, this is the opposite, it's reflection, is opposite. So we can see how vectors also relate to transformation now, because we will look at the mirror image. So that will be an image. So how do we basically represent this in vectors as well? So I'm just giving you this. So this is the image, and this is the inverse of the image. And normally when we refer to things as inverses, that's basically where we multiply the image by -1. Okay, so the opposite of any number, not really, I don't want to call it the opposite, but it will be the opposite on a number line, is that number multiplied by -1. Okay, so we will I hope that we saw that one. Okay, we didn't see that one. Let's go back. I thought, okay, it showed, so it's fine. I just thought it didn't show the image that we drew, but I see it showed the image as well. So the explanation is fine. Sorry for that delay. As I said, we have a short delay in some of our lessons, so I'm not always able to see clearly what is going on. All right. So in this case now we have explained our image line. So what it means basically for us to do is, when we ask you find the opposite vector of this one. So in here we have our vector u, which is depicted as -4, 3. And to find the inverse of this vector, we basically just have to take our vector u, which is that one, and we will basically multiply it by a -1. So I wrote in the multiplication of that vector, and it produced a vector called vector v. All right, so if you have noted that my vector u is ab, the one we started with, and I wanted to find the opposite of that vector, I just took that vector's coordinates and I multiplied by a -1. -1 is what we use to find our inverse. Okay, so I multiplied it by that -1, and it produced another vector called vector v, which you can see on this side here. Okay, so the inverse of this vector. Now let me just also write in the direction. This vector was moving in that direction, and this vector is moving in that direction. So if we look at our column vectors here, what has changed? So this is also basically an introduction to vector multiplication by a scalar quantity. So the scalar quantity is the -1. We will be looking at that one as well. Scalar quantity is -1, and then we multiply that -1 with our vector here, and then it produced this one. So -1 times -4, negative and a negative gives you a positive, and then a -1 times a -3, a positive and a negative gives you a negative. So it's just flipping the vector over. Please do note, if we calculate the magnitude of the vector, we will get the same magnitudes for both of them, because the distance between the points are exactly the same. Okay, we did not change the distance. If you note, 3 squared is the same as -3 squared. You will both get 9 for these answers. So the magnitude is the same. Only thing that has changed is the direction. And you would have noticed now if we point it in this direction, then the opposite for this direction is the other quadrant. So we have our first quadrant here, we have our second quadrant here, and we have our third quadrant here, and our fourth quadrant here. The 4 doesn't look like a 4. Let's make it a 4. And we have our fourth quadrant here. So if you are in the second quadrant and we ask you to find the opposite of that vector, that means that we will now find a vector that is located in the fourth quadrant. So this is what the student mentioned a while back. Let me just also bring that image up, and let me just show you again. So if we are looking at our vector in this sense, that you would notice that for all the opposite vectors that we are having, if we are in the first quadrant where everything is positive, if we have to find the opposite vectors there, we will move into the third quadrant here. So you will also see in this image that we provided to you, I try to keep most of the colors the same as well, so that we can try and see, okay, we have a opposite vector going into the other direction. Then that is one way of looking at it. However, your knowledge of what we call angle properties is also needed here. If we look at some angle properties that we will have, let me just show you a short example. Line and line. So in our angle properties, we say that opposite angles are equal, right? So we have an A here, that means we will also have an A here. Okay, if we have a 7 here or an F, then we will also have a 7 here or an F. Opposite angles are equal. Okay, we remember this rule from angle properties that we have done. So this opposite angles that are equal is basically stating the fact that the magnitudes of these opposite angles are the same. So the sizes are the same, okay, but the direction is not the same. Okay, so the direction is what differs, but the sizes are the same. So we will also make use of this method as we proceed with the lessons as well. I've noticed that we have reached a little bit longer, but it's important to conclude this lesson as well. So for our final part, we will be looking at vector addition and also vector subtraction. Okay, so vector addition and vector subtraction is the last part for this lesson. So if you bear with me, we will be done shortly. So let's just look at adding vectors and also subtracting vectors. And we've also mentioned already multiplication by a scalar quantity already. The multiplication that we did was with the -1 to find the opposite vector. Okay, so you take your number that you are multiplying it with, and you just say this number multiplied by the top and this number multiplied by the bottom of your column, and that's what we have. So in adding vectors, okay, vectors can be added using one of two methods. Then we have a parallelogram method or the tail to top method. That one is vector addition is a commutative property of addition, which means that A plus B is the same as B plus A. So this is a commutative property of vectors of addition is important to mention as well. If we say A plus B is equals to B plus A, 4 plus 2 is the same as 2 plus 4. That's basically what commutative means. To add vectors using a parallelogram method, two arbitrary vectors A and B can be moved so that their tails are coincident. Their tails share the same point, a parallelogram is drawn using two vectors. The sum of the two vectors R is the vector drawn from the coincident tail to opposite vertex of the parallelogram. Okay, so we will explain that one in a short while. Since a vector is defined by its magnitude and direction, vectors can be translated to any position as long as the magnitude and direction of the vector remains the same. Okay, so this property here we will also look at shortly in terms of what it really entails, and then in terms of subtraction of a vector. Okay, we can also say the following: subtracting a vector from another can be seen as adding a negative vector. So now we are speaking about a negative vector again. So we will just explain this one in detail, and then I believe we will be ready to have it here. So this is the slides that I will post on the Google Classroom to help, but let's look at it in on the demonstration board so that we can see how this doing vector addition and subtractions work as well. Alright, so we will go back to our drawing board, and over here we don't need this one now. Let's just create a vector. Okay, and that would be a not a line, a vector. Okay, we are almost done with the lesson, so thank you for bearing with me. Alright, so over here I have a vector AB. I just want to see, okay, I can move it. So let's see. Okay. Okay. So I've duplicated the vector AB to be A1 and B1. Alright, but that's not really a problem. So I'm going to have another vector here. Okay, let me just remove this vector so that we have different two vectors that we have here. Okay, so dealing with vectors, our first method here is the parallelogram method. Okay, so within the parallelogram method is basically we have these two vectors here. Okay, let me just change the direction a little bit of CD so that it looks like something here. So we have these two vectors here, and these two vectors that we have here, we need to add them together. Okay, there are two different vectors. We have a U and a V. So our task is to add U with V. So let me just also write it in here. We are going to say U plus V. That is what we want to do. Okay, so U plus V, we are adding the vectors. So the first method is to draw a parallelogram using the two vectors. So how do we draw a parallelogram? We basically move our vectors to form a parallelogram. So our vector C and B will go to one point. Okay, that is the point we have, and then I'm going to duplicate C and D. Can you see I duplicated it, and I move it to the other end there. Okay, more or less, and then I will duplicate A and B and move it to the other end over there. So this forms a type of parallelogram. Okay, so once we have formed this type of parallelogram, then we will now make a new vector by basically joining one end of this parallelogram to the other end of it. So this vector now will become vector W. Okay, so we have now created a new vector. So this is basically the addition of vector A, B, or vector U and vector V produces a new vector called W. So in another form, when we add a vector by observation alone, okay, when we add two vectors, okay, it makes a form of a triangle if the vectors are diagonal. All right, if the vectors are skew, okay, they will form a triangle. So what happens if the vectors are not skew? Let's say we have vector EF here, and we have another vector GH here. So if we add two vectors that are not what do we call skew, so basically what it means is let's just remove that one, it's not what I wanted. Okay, what it means is basically we will move this vector to that point again, and now you can see adding vectors that are in a straight line, it just makes the line longer. All right, remember, let's use that real life example. If we have football players again, and we have 4 players in this case, player 1, 2, 3, and it's passing the ball in a straight line. Player G passes to H, H passes to is it E, and E passes to F. So you can see the ball has traveled from G now to F. That's now adding a straight line vector. This can be the same for when the vectors are horizontal. Okay. However, when we are adding vectors in terms of diagonal vectors, then it will look like this a little bit. All right. So there is another method as well. This is the parallelogram method that we have. The second method of the vector is in another sense. Please note, if we are saying we are doing vector subtraction, what it means is if we look at the vector BC, okay, let me just move it. We will look at the inverse of BC, and then we will add it there on. So let me go to another one so that we can just not always, let's just go back here and back so that we don't also lose that information that we have there. Alright, so I hope that the parallelogram method is actually also mentioned, but I would just like to show you a straightforward way of adding vectors. Sometimes when we are dealing with transformations, we will ask you to draw it in on the Cartesian plane, the addition of the vectors. However, when we want you to get the simple answer, we will just ask you to do the calculations itself. So for this example that we will have, we will just do a simple calculation itself as well. So I have AB, we will make that one a vector. Okay, and I will add it to another vector. Which direction should the vector go? Let's go this direction. Okay, so we will add it to CD in this case. Okay, so my point being is that since we know that the vector U has a column vector of 3, 3, and the vector V has a column vector of 3 and -2, and when we are adding these vectors, in simple terms, we can just add the columns to each other. You add the top to the top, you add the bottom to the bottom, and that will produce a resulting vector. So what I mean by the following is, we say we will have V plus U. Okay, so you saw that when I put in my calculator V plus U, it produced a different vector here. Okay, so we add this vector to that vector. So let's just look at this vector and try to find out the column vector for this one. So if I said U is 3 and a 3 on 3 rows, 3 columns, 3 rows, 3 columns. So let's look at this one again. So it's a 3 plus a 3, that gives me a 6. Can you see? So that's the 6 that we get there. And then we have a 3 plus a -2. Okay, so that gives me a 1. 3 plus -2 is 1. So we have now a new vector, this vector W, which is this one here. Let me just use the moving tool, which is the, unfortunately W cannot move. Okay, you can see now the resulting vector here, 6, -1. All right, let me just try and recreate that vector. Okay, and I can move it around so that I can show you how they all fit. Okay, it doesn't want to move from the center. Okay, I just want to move it a little bit, so I'll create a equal vector that is equal to that one that I am able to move. So we said we should have a 6 and a 1, so that means we should have 6 rows and 1 column. So that's 1, 2, 3, 4, 5, 6, somewhere there. So this is the vector that we have created, and I can move it. So just to confirm, they are equal. Okay, so you can add the column vectors by themselves, and that will give you your resulting vector, and this is the resulting vector. So we have another method that we call the head to tail method, where we take vector C, correct, you put it, the tail of vector C, V, let's call it vector V, the tail of vector V goes to the head of vector U. So that's the tail and the head, you put it in like that, and then you connect the tail of vector U, right, you draw a new vector. Let's draw a new vector, not a vector. So a new vector can now be drawn from the tail of B to the head of V. So this vector here, which is now a new vector, can be drawn from the resulting vectors that we have there. Okay, so if I take this vector here and I place it there, you can see it's exactly the same. Okay, they are equal. All right, so this is another way of showing a vector addition by using the head tail method. This is called the head and tail method. Alright, so you saw that this one is coming from our addition, which we normally did, and it's exactly the same same size as our new vector B. Okay, so these two vectors are equivalent vectors regardless of where we move them around. We said that we can move them around. Alright, finally, in terms of vector subtraction, we will have one example for vector subtraction, and then we will be basically calling it a day. Other than that, more operations, we will be looking into questions as well. We will post some of those questions online and so forth. Most of the things that we are doing here, we are going to combine various ones of them into one single thing. So we will do combinations of some vectors that we have as well. So the last example is just on vector subtraction, and then we will call it a day. So let me just draw in a vector EB. Let's just draw in another vector. Let's use this quadrant here. We have that one, and then we will use another quadrant which is here. Let's make it a little bit different so that the two vectors are different. Alright, so we are now basically looking at vector subtraction, and for vector subtraction we will have these two vectors that we have here around. So I know when you get your examination paper, you will not be able to move the vectors around freely, but we just want you to do, if you cannot move it, you can always draw it in. Remember, this is one of the rules I said. When you have a shape or a paper, you can always draw in the same vector or the equivalent vector into this shape. So when we are doing a vector subtraction, correct? Okay, vector subtraction means that, let's say we are subtracting vector u from vector v. Okay, so our notation will look something like that. We are saying it's going to be u minus v. Okay, that is what we want to do now, u minus v. All right, So how do we do this? We basically change this u minus v into vector addition. Okay, we don't work with negatives. Sometimes it's confusing, so we change it to an addition. Okay, how do we change this to addition? Is basically we will write it as follows. I will write it down here so that you can see. We will say it will be u plus is now our new addition, and in brackets we will say negative v. So that is basically how we are looking at vector subtraction. It's u minus v, but we change it to u plus negative v. So we don't have a negative v here. Remember, I told you that when we are saying negative v, it means it's the opposite of CD. So in here I can now put the negative v in so that we can draw the negative vector, or we can just see what is v. What will the negative vector or the opposite vector of v be? So it will be the vector v times negative 1. So we will multiply it by negative 1, a scalar of negative 1. So the 4 will be a positive and the 2 will be now a negative. So what that means is we will have a vector. We will have a vector that goes in this direction. Okay, we will have a 4 and a negative 2, which is this direction. All right, so just to undo that one. So our negative v, okay, can be written as this w. Okay, but if you don't like the w, we can just say here, what do we have? We have vector v, which is our vector v. All right, and we will be multiplying it by, we will multiply it by a negative 1. Okay, and that's what we get there. That will give us our negative vector. So you can see this is exactly the same vector that we're having here. All right, so when we are doing vector subtraction, first we change one of the vectors to the opposite vector, and then we follow the steps of the either we will make use of this one and now not anymore this one anymore. We'll make use of this one to do vector addition. So this is our negative v, so we must add it to u. So we'll use the head tail method. So the head of that one goes to there. Please note you can also use head tail method in another way. It does not matter, you will still end up with the same answers. Okay, so we have right there, and then after we do the head tail method, then we will now get a new vector which is supposed to start from here to the head of the other one there. So now we have a new vector called vector b, and that's what we have there. In another sense, we can also just now say we are going to add vector u to vector w, and that will produce our resulting vector here, which is that answer that we see there as well. So this vector c is what we get from adding these two vectors here. Okay, so vector subtraction, u minus v, we change it to addition, and then we work with the opposite vector of the one that we are using to subtract. Okay, and then we just do addition and the steps are the same. Okay, so there's just one additional step. Change the negative to a positive by having a plus minus. Please note this, if you do your mathematical algebra, it will result back to u minus v, and that's how we easily do it. If drawings is a bit difficult, we always advise you to always first use the column vectors, do the subtraction from the column vectors, and then we will get the answer easily. So if I looked at vector u and v, which was the ones we did on top here, if I had to subtract these ones from each other, we said u and v. So in v I have a in u I have a 3 and a 3, that's what we were having there, and v I had a negative 4 and a 2. So if you say 3 minus negative 4 will give me a positive 7. Is that not so? it will give me a positive 7. So 3 minus negative 4 is 7, and then you look at 3 minus 2 will give me a positive 1. So you can see just also by subtracting the numbers top from top, bottom from bottom, you will also get a resulting vector that's looking at the same ones that we're having here, a positive 7 and a positive 1. And that means that our vector will be in that direction. Please note, vector C and B are exactly the same vectors, regardless of where they are at this point in time. Alright, so again, I will repeat that one. When we are drawing this method, it's just to show you a graphical version of how vector addition applies. And we can always just use the numbers to do our vector addition and vector subtraction that we have here. To note something very important, when we punched in our equations here, it produced C and A. C and A is a result of our vectors. A is the opposite of vector V, and C is the subtraction of U minus V. These vectors that are starting at the origin, position 0, and going out, these vectors is what we call position vectors. We call them position vectors because they are positioned using the origin. And remember that we said that we want to move the origin to a point in a vector so that we can count the blocks easily. So position vectors makes it easy to count. You just use what is the y-axis. The y-axis here has a value of 1, so that means your column is 1. What is the x value of the x-axis? The x-axis is having a 7, so your rows will be having a 7. So when you represent your vector, it will be based on a position vector, where we have for the y value, which is the 1, and for the x value, which is the 7 in this case. Not a 1, but a 7 in this case. So that will be the position vector because it's from position 0. In this other one, we have also from position vector here. We have a, let's start with the x values because it's the first one. So for this position vector A, we have a row of 4. That's the x coordinate is 4, and the y coordinate is a negative 2. So position vectors allows us to get the coordinates or the magnitudes or the sizes of the quantities that we have for those vectors very simple and easier. Okay, so that's why I mentioned in the previous slide that if we want to find the vector sizes or magnitudes here, then we bring the Cartesian plane position 0. The origin must start at one of the points, and then we will start it normally in the direction that it points in. So please also note that the position vector helps us also with our quadrants. In our quadrants, it means everything in here must be positive. If it goes in this direction, everything in here must be negative. If it goes in this direction, we have a negative positive. If it's in this direction, we have a positive negative. So it fulfills that rule of our what we call our quadrants that we have looked at as well. So that's for position vectors that we have. All right, I think we have exhausted most of the points. What we will post on the Google Classroom will be just various questions on vectors and how you can answer some of these questions as well. And we will be having a task as well on this vectors and how we will apply. Some of the things that we have mentioned here is already introductions into transformations and also some introductions into matrices, and some of the skills you have learned here you will be using a lot again. So just bear that one in mind, and I hope that you have learned something from this. If there are no more questions, thank you for tuning in. and enjoy your Easter weekend as well. We will have a discussion on Google Classroom regarding on times of the classes as well, and how we should move forward as well regarding the weekend. And I think next week should be the final week before we hear anything about school starts as well. So we will also keep you informed on what is happening there. All right. If there are no more questions, thank you for tuning in, and good luck. I will just post up some questions regarding vectors from previous examinations that you can also make use of as well. All right.